Hey guys, how's it going? So today we're going to be doing a ordinary differential equation. It's in the form of a vector equation where x prime is equal to ax, where A is a matrix filled with numbers. So here we have x prime is equal to ax, where A is 115, 151, and 511. So how do we solve these types of differential equations? First of all, you should be able to recognize that this is a very good question. We're just going to apply our linear algebra knowledge here and move from there. So we're going to find the eigenvalues and its corresponding eigenvectors. So I'm going to write that down in text. First, find eigenvalues and corresponding eigenvectors. So A is equal to this. We need to say A minus I lambda. A minus I lambda, so it's like lambda times the identity matrix is equal to 1. Okay, so I'm going to do it a bit slower because I want you guys to see the full effect. 115, 151, and 511. Minus I, so I is just like, yeah, so lambda 0, 0, and then it's 0, lambda 0, 0, 0, lambda. Because lambda is a scalar value and the identity matrix is like these with 1, so 1 times lambda is like lambda, like that. And that is equal to 1 minus lambda, 1, 5, 1, 5 minus lambda, 1, 5, 1, 1 minus lambda. And to find the eigenvalues, we need to set the determinant of this A minus lambda matrix equal to 0. So I'm going to turn off the heat thermal on my, it's pretty hot in here. Okay, so det A minus I lambda, det determinant, det short for determinant, A minus I lambda if it hasn't become obvious to you guys, eigenvectors and eigenvalues can only be found on square matrices where it's n by n matrices. Okay, so that's equal to 1 minus lambda, 1 minus lambda times determinants of these 4 values. So 5 minus lambda, 1, 1, 1 minus lambda. Minus, so it's like positive this, negative this, positive this. So minus 1 times the determinant of 1, 1, 5, 1 minus lambda. 1, 1, 5, 1 minus lambda, plus 5 times 1, 1, 5, 1 minus lambda. Okay, so let me see if, no, sorry, let me backtrack. I made a slight miscalculation. 1, 5 minus lambda, 5, and 1. So 5 lambda, 5, and 1. These 4 values. Okay. Now, okay, so that's equal to, and this is equal to 0. So let's expand this. 1 minus lambda. 5 minus lambda times 1 minus lambda minus 1 is lambda squared minus 6 lambda plus 4. Minus 1 minus lambda minus 5. That's negative 4 minus lambda. Plus 5. Okay, this is 1 minus 25 plus 5 lambda. So that's negative 24 plus 5 lambda. And that's equal to 0. Okay, when we expand this out, you get negative lambda cubed plus 7 lambda squared minus 10 lambda plus 4. Plus lambda plus 4 plus 25 lambda minus 120 is 0. Simplifying this further gives you, okay, so you can simplify this. You simplify this. And I like to tend to have the one where the power, the degree of the polynomial has a positive coefficient. So I'm going to simplify this and then multiply both sides by -1. And I get lambda cubed. You don't have to flip, make the coefficient of the leading power to be positive, but I just like to do it that way. It's an old habit of mine. Lambda cubed minus 7 lambda squared minus 16 lambda plus 112 is 0. Now, at this point, you can use the factor theorem, but I've got a much faster way, and that's to do it factor by grouping. So here, the most common denominator, you can factor out a lambda squared on the first 2 terms, and that's a lambda minus 7. And here, you can factor out a negative 16, and then get a lambda minus 7. That looks like a T. Minus 7 equals 0. Lambda squared minus 16 times lambda minus 7 is 0. Okay, and then when you, so lambda squared minus 16 is 0, lambda minus 7 is 0. We have 3 eigenvalues. Lambda 1 is equal to 4. Lambda 2 is -4, and lambda 3 is 7. Okay, I'm going to give you guys a few seconds to look and process what these eigenvalues are before I go find the corresponding eigenvectors, because I need some space to find the corresponding eigenvectors. I've got the eigenvalues tracked in my notes. So 3, 2, 1. Okay, hope you guys had enough time to look at it. We're now going to erase everything except the original question. All right, so when lambda is equal to 4, so A minus I lambda, when lambda is equal to 4, the corresponding matrix is 1 minus 4, so -3, 1, 5, 1, 5 minus 4, which is 1, 1, and 5, 1, -3. And to find a corresponding eigenvector, so we have this matrix, this A minus I lambda matrix, and then x1, x2, x3, and we say it's equal to 0. It's like a homogeneous set and such. Now, I'm going to do something like this. So I'm just going to write out the original matrix. Usually when you do linear algebra, I'm just going to write something down first. Okay, so 3, 1, 5, 1, 1, 1. Okay, 5, 1, -3. I'm not going to include the thing here and say 0, 0, 0, because regardless of the operations I do, like it's this part, this column will not change regardless of the operations I do on the rows 1, 2, and 3. So I'm just going to omit this column. Usually for in homogeneous equations where it's like it's not equal to 0, I don't do it, but when it's equal to 0, I can just omit it out. So yeah. All right, so the first thing I'm gonna do, I like to diagonalize from left to right. So I'm going to focus on the first column with the 3x3. Whenever I do like a square matrix and solve like equations, I like to go from the left, focus on the left column to the right column. And for the leftmost column, I focus on the lowest common factor. So lowest common factor of 3, 1, and 5 is 15. And this is a good rule of thumb for any n by n matrix in linear algebra. So, okay, so 3, 1, and 15. That's, okay, I'm going to make them all like 15. So -3 times -5. Okay, so 15. The first row should be multiplied by -5, all elements there. So -5, 25. To get 15 on the second row, I'm going to have to multiply everything by 15. So 15, 15, and 15. And the third row, 5, 1, multiply by 3 to get 15. So 15, 1 times 3 is 3, and times -9. Now, I'm going to multiply, no, sorry, I'm going to subtract everything, the second row and the third row by the first row. So I'm going to write that down actually. R2 minus R1 goes to R2. Second row minus first row goes to second row. And the third row minus first row goes to third row. R3. Okay, so that is okay, so the first part, 15, -5, -25. Nice. Oh, this should have been a neg. Wait, hang on. Something's a little inconsistent with what I have. Oh, I forgot to put a minus sign there. Okay. Okay, yeah, everything's good now. So R2 minus R1, 15 minus 15, 0. 15 minus -5 is 20. And 15 plus 25 is 40. Okay, and lastly, R3 minus R1 goes to R3. 15 minus 15 is 0. 3 plus 5 is 8. And -9 plus 25 is 16. Okay, I think we can factor everything back to it originally. So -15, 5, and -25, I'm going to divide that by, divide row 1 by 5. So that's 3, -1, and -5. I'm going to divide row 2, all the elements by 20. So I get 0, 1, and 2. I'm going to divide everything in row 3 by 8. So I get 0, 1, and 2. And I'm going to eliminate a row or make them all zeros. I like to call it eliminate. I always like to eliminate the bottommost row when finding an eigenvector. You don't have to, but I want to. So that's, I'm going to say R3 minus R2 goes to R3. And these will all cancel out to 0. So that implies, let's see, so 3, -1, 5. 0, 1, 2, and 0, 0, 0. Now, I generally, when I like parameterize eigenvectors, I like to have my rightmost variable, x3 or x2, depending on if I'm doing a 2x2 or 3x3 matrix, as the parameter t. So for this reason, I like to have my x1 and x2s equal to something times t. So I'm gonna do this. You'll see what I'm gonna do in a sec. I'm gonna cancel -1 on the top so I can have x1 in terms of x3 or t. So what I write is R1 plus R2 goes to R1. And doing that, that gives you 3. Okay, so R1 plus R2. 3 plus 0 is 3. -1 plus 1 is 0. I wanted to cancel this out. I have 5. Sorry, that should have been a -5. -5 plus 2 is -3. And then everything else stays the same. So 0, 1, 2, 0, 0, 0. And lastly, last but not least, divide row 1 by 3. So 1, 0, -1, 0, 1, 2, 0, 0, 0. And I'm going to put in the final column of zeros, 0 vector. And these are your x1s your x2s, and your x3s. And like I said, when doing an eigenvector, I always like to have the rightmost variable as my parameter t. So here that means x3 is t. x2 is negative 2x3, because x2 plus 2x3 is 0. So x2 is negative 2t. And x1 minus x3 is 0, so x1 is just equal to x3, which is t. And the corresponding eigenvalue is 1, 2, 1. So t, 1, 2, 1. And let's do it for the other two eigenvalues now. At this point, I encourage you guys to pause the video and try it on your own. But at the same time, I write this slow enough so you go along with me. It's good practice anyways. So let's see what happens when your lambda is negative 4 instead. Okay, so negative 4. I should have left the x1, x2, x3. Now I have to put it back in. Okay, so then that is equal to 0. Let's focus on this. I'm going to leave this part in for the next eigenvalue when I'm finding the eigenvector. Okay, so let's rewrite A minus I lambda. So 3, 1. Oh, shoot. No, crap, I did have to, in fact, erase everything. All right, let's do it like this. A minus I lambda, 1 minus negative 4, that's 5. 5, 1, 5. 1, 5 minus negative 4, that's 9. 1, 5, 1, negative 3. Okay, now let's rewrite this. Okay, so 5, 1, 5, 1, 9, 1, 5, 1, negative 3. All right. So the first thing we have to do is we're gonna do this. I'm gonna do everything in one shot and make the coefficients on row 2 and 3 for the x1 to be 0. So what I write is 5 times R2 minus R1 goes to R2. And then it will make this coefficient 0. And R3 minus R1 goes to R3. Okay. So that counts. Okay, the first row stays the same. Nothing happens there. 5, 1, 5. That's a 9. That's not a 4. So 5 R2. So 5 times 1 minus 5, that's 0, just like we wanted. 5 times 9 minus 1, that's 44. 0, I think. Wait, hang on. 5, yeah. 5 times 9 minus 1, okay. 5 times, yeah, that's your R2. R3, yeah, 5 minus 5 is 0. 0. Wait, why does something look so weird? Oh man, I'm getting way ahead of myself. 1 minus -4 was supposed to be 5. This was supposed to be a 5, damn it. Sorry about that, guys. Okay, so that was 515. Yeah, okay, this is more how I remember it. The third row was supposed to cancel out entirely. All right, and you can do, you know what I'm gonna do? You can go further and then just divide this row 2 by 44, but I think I'm gonna stop here and start parameterizing it now. Before you parameterize, make sure you include the 0 vec column. Call this x1, x2, x3, set x3 equals t, and go from there. Okay, so first thing, this is slightly different from the first eigenvector. Look at the second row. 44x2 is 0. The only plausible solution is x2 is equals 0. If okay, and x3 is t. Look at row 1. 5x1 plus x2 plus 5x3 is 0. But x2 is 0, so you can just say, and then 5x1 plus 5t is 0, because x3 is t. Divide both sides by 5 and like do some arranging around, and you get x1 is equal to -t. X1 is -t. So based on this, that the eigenvector is -1, 0, 1. T, -1, 0, 1. Let's do one more for lambda equals 7. I still have to erase. All right, so a minus I lambda for lambda is equal to, I have to change this to b. Okay. 1 minus 7, a minus 1 minus 7, that's -6. 1, 5. 1, 5 minus 7, that's -2. 1, 5, 1. 1 minus 7, that's -6. Okay, so we have this, and we can just take this a minus I lambda matrix out in the front and do some manipulation, the same manipulation tactics I've been doing for the past 2 eigenvalues. -6, 1, 5, 1, -2, 1, and 5, 1, -6. All right, so for this one, yeah, we want these 2 values in the matrix to be 0. So, but this time the lowest common denominator for 1, 5, and 6 is 30. So I'm gonna make them all correspond to 30 and for x1. So I'm gonna multiply the first row by -5. So that's 30 1 times -5, -5. Okay, and 5 times -5 is -25. Okay, 1 times 30 is 30. Okay, so then set row 2 would be 30, -60. 30, you multiply everything on row 2 by 30. And you multiply everything on row 3 by 6. So this is also 30. 5 times 6 is 6. And -6 times 6 is -36. Yeah, that's right. Okay, so R2 minus R1 goes to R2, and R3 minus R1 goes to R3. That should have been R1, not R2. I'm going to erase that right now. Okay, and that is equal. So that leads to, so the first row stays entirely the same. Actually, you know what I'm going to do instead? I'm going to divide the first row after doing these two operations. I'm going to divide the first row by 5 and get back to its original value times -1. So R1 over 5, R1 goes to R1. Okay, so that 1 over 5 R1 goes to R1. 6, -1, -5. R2 minus R1 goes to R2, so that's 0. -55 and 55. And here it's 0. Or let's see, 0. R3 minus R1. No. Sorry, yeah, R3. 11, -11. Okay. 11, -11. And -55 and 55 and 11 and 11, -11, they're proportional. Rows 2 and row 3 are now proportional to each other. I'm going to do a bunch of steps in one step. And I'm going to write it down first, and you'll see what I'm doing in a sec. So the first row, nothing changes there. -5, 0, 1, -1, 0, 0, 0. So row 3, I eliminated row 3. And essentially what I did here was I basically divided rows 2 by 55, everything in row 2 by 55, and I divided everything in rows 3 by 11. So I had -1, 1, and 1 and -1 here in these respective entries. And then I subtracted row 3 by row 2. And then I put that into row 3. So yeah. Now, what I can do is I'm going to get rid of this value so I can have x1 purely in terms of x3. So to do that, I'm going to say R1 plus R2 goes to R1. Okay, and then that is equal to 6, -1, sorry, 6, 0, R1 plus R2, that's -5 plus -1 is -6, 0, 1, -1, 0, 0, 0. I'm going to divide row 1 by 6. I'm going to erase this part because it's getting in the way of my calculations. So 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0. And say that's 0, 0, and 0 here. Okay, and then call this x1, 2, and 3. Now, so x3 is equal to t, x2 is equal to x3, and x1 is also equal to x3. So x1 equals x2 equals x3 equals t. So the corresponding eigenvector is 1, 1, 1. Now, we have our eigenvalues and eigenvectors. To put them in the solution for ordinary differential equations, what you do is basically this. So we can now put in our solution. So x of t is equal to, you first say C1 and then the first eigenvalue. So it was 4. So e to the power of 4t. And then the eigenvalue was 1, negative 2, 1. So you write it like this: 1, negative 2, 1. And then our second eigenvalue was negative 4. So C2 e to the negative 4t. And that corresponding eigenvalue was negative 1, 0, 1. And our third eigenvalue was 7. So C3 e to the 7t 1, 1, 1. And this is our final answer. So now you are able to solve any ODE in the form of x prime is equal to ax, where a is a matrix filled with numbers. And you know what? I'm going to actually give you guys, I am going to give you guys a practice problem. I'm going to give you guys a practice problem. I'm not going to do it because I want you guys to do it. I am going to, here's a practice problem for you guys to try at home. X prime is equal to negative 5, 4, 6, 5. X. And the answer, the corresponding answer to it is x is equal to C1, 1, 3, e to the 7t plus C2, negative 2, 1, e to the negative 7t. I'm not going to show you how to do this. I want you guys to try this at home by yourself. I only give you the final answer to this question. Okay, so that's all for today. I hope you guys liked this video. I love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.